There is another interesting method to generate dead time. Let us have a look at that. It's a pretty simple method, can be easily implemented. Consider a triangular carrier which is in this form, as I was showing, plus and minus, and with this is compared some modulating signal Vm. This red waveform is the low frequency modulating signal, blue waveform is the high frequency triangular carrier. So I will draw one more axis and project the pulse width modulated waveform onto this axis. So at every point of intersection between the modulating signal and the triangular carrier, let us drop down the time projection. So here, this is another point of intersection, here, here, here. And we can now draw the PWM waveform. So let us say that Vm, that is the red waveform here, is given to the plus input and the triangle is given to the minus input of a comparator. So you will see that during this period, the output of the comparator is high. And during this period, when the triangle is higher than the modulating signal, the output is low, and so on. Here, the modulating signal is higher than the triangle, therefore you see the output as high, and then again low, high, so on. So this is the pulse width modulation waveform that you would obtain if you compare this modulating signal and the triangle. So now what I am going to do is have one more triangle slightly offset from the previous triangle, like this. So this green line that you see, this green triangle lines, is a new triangle, same frequency, same amplitude, but offset from the previous one by a very small voltage. Now with this triangle also I can make a comparison of the same modulating signal. So let us do that comparison, and let me project the points of intersection of the modulating signal with the new triangle or the green triangle. So these green lines are the lines of projections onto the time axis. So like this you have the projections onto the time axis. And when the modulating signal is higher than the green triangle, then you can see an output that is high. And when the modulating signal is less than the green triangle, you will see an output that is low. And so on, you will see the outputs in this fashion. Now I will have one more time axis like this, and what I am going to put there as the waveform, I will just explain. Before that, I want to indicate that these waveforms, let us name them. I want to indicate this red waveform. The low frequency red line waveform is the modulating signal, call that one as Vm. I am going to indicate this green triangle as the upper triangle, V triangle U upper, and the blue as V triangle lower. Now with respect to these variable names, let me draw the op-amp. So for this waveform, the output is coming from this comparator in this fashion. So this plus, minus, I'm going to have the modulating signal Vm here, this one. And here I'm going to have the triangle. Which triangle? The one which is in blue, and that is V triangle lower. And the output of this would represent this pulse width modulation waveform. Of course, this is clipped or clamped by a clamping circuit, which I will show later. This PWM waveform is coming from Vm at the plus and V triangle upper at the minus. So this will be this one, this green pulse width modulation wave pattern. Let me draw the third comparator, plus and minus. So to the minus, I give Vm, and to the plus, I give V triangle lower. So basically this is the inversion of this, inversion of the blue waveform. So whatever this blue PWM is, this is the inverted of that one. So let me draw this inverted waveform like this. So you see that this and this waveform together form our requirement. So let me complete this. So you don't forget the VCC and VEE, plus and minus 15. And you have to have a clamper, Schottky clamper like we discussed before, so that this becomes just a unipolar waveform like this. Power supply followed by a clamping circuit will give you a unipolar waveform like this, and a power supply clamping circuit will give you a waveform like this. This is given to VG1 drive and this is given to VG2 drive. So you see that these two PWMs do not have a common transition line. There is a dead time, and the dead time value can be adjusted by adjusting the level translation of the two triangles. So that will give you the dead time adjustment parameter. The level translation offset is directly proportional to the dead time. I have opened the PWM analog schematic. This is something we have discussed before, and then we have also implemented and run the simulation in ngSpice. To this, we can extend this schematic to incorporate the alternate dead time generation that we just now studied. So let me include some components. I will go to the add symbol. I need to pick up some resistors and op-amps. So from the my blocks library, I will pick the op-amp. I will take a couple of op-amps. I will need one more op-amp. I will incorporate it here. Right. So what I will do is I will shift this a bit to the side, pick up this op-amp and place it here. Pick this also and place it here. Okay. And let me get in some resistance. R. Then one more resistor. I need to make a bridge. I will explain to you why I am going to make a bridge now. This is the part where I want to give the offset. Okay, so this is the bridge. I will change the cursor and pick this label. I will copy that and place this label here. This label will give you VCC, and this label I will need copy and paste, which will give me VEE, the minus 15 volts. Now I can join this to this. So I have resistors connected from VCC to VEE. How do I give the offset to get two triangles? Now that is the important point. So if I look at this midpoint, let me add. This is a node. I will call this as node low and place it here, and I will have node up and place it here. I'll also connect them up. So the center point is basically the voltage division between these two resistors. So what I'm going to do is give values to these resistors, which will make it clear. Now let us say that if I make everything 10K, 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 and 10K. So the center point is that now if this is 15 volts, is minus 15 volts, center point will be at 0, this will also be at 0. But I want a slight offset. So what is going to happen if I make this 10.1K? Make this 10.1K and this is 10K, which means this point is slightly above 0. Now here I make this as 10K and 10.1K. So if you see that this point is slightly below 0 and this point is slightly, this attenuation with respect to ground, this point is slightly below 0, superposition of this and this, and superposition of this and this with these resistors, this point will be slightly above 0 because this is 10.1K and this is 10K, and this attenuation factor here is slightly less than 0.5 and this is slightly greater than 0.5. So when I add this value to this triangle, which you get here, this is triangle. To this triangle, if I add this, there will be a slight shift of the resultant triangle above 0. And if I add this to this triangle, there will be slight shift of the triangle below 0. So this way I will get two triangles which are offset with respect to each other. So that's what I want to do. So let us do that. Let me have these two adder circuits, one for upper and one for lower, and then I need few more resistors. So I want to take this triangle waveform and so let me pick up few resistors. I want resistors here and I want these. Let me place the resistors first and then make the circuit. You will understand the circuit. I'm going to make simple differential amplifier straightforward differential amplifier, which all of you are familiar with. And you will see that this can result in a very simple delay generation or dead time generation circuit. So I have almost all the components here, so we'll keep that, and I need to give in the VCC, copy, and I will paste the VCC. Maybe I'll rotate it so that the space is saved. Then I will copy this also and paste it here and rotate it. Yeah. So likewise, I can copy these two and place them here also. And we can make some adjustments here so that it is easy for us to place the components and the connection wires. The connecting wires, we'll place it now, and I need the 0 reference. I'll need one here, one here for now. Let it be there. So now let me connect them up. Okay. So let me make some space here. Yeah. Take the wire cursor, make the connections. Like this. Connect VCC, connect VEE, connect all this. So you see the differential amplifier is evolving. So this is the differential amplifier. Connect VCC and VE like this. And the 0 node. Yes. So I have connected the two difference amplifiers. Now I will take this triangle waveform, place it here, then again copy this and place it here, connect these two nodes. So I have connected the triangle waveform to the plus side of the differential amplifier, and now to this I will connect these offsets. So let us say the lower offset, minus offset, I will connect it here, and the offset which is above 0, I will connect it here. I need to move this forward a bit. Okay. this back a bit. Make the connection, interconnection here, and this interconnection. I will now incorporate these two nodes here. The output here will be one triangle, this will be another triangle. But here, what is the output here? If I keep all as equal resistances, the output is difference between these two voltages. So here it will be V triangle voltage minus NDLO. But NDLO is slightly negative, slightly below 0. So it will become minus of minus that whatever that slight DC offset. So this will make the triangle shift up. So this will become the upper triangle. Here it will be triangle minus ND up, which is slightly greater than 0. So it will make the triangle go slightly below 0. So this will become the lower triangle. So I will incorporate these labels here. So I will say T up, triangle up, this is triangle up, and this is T low. This is triangle low. Make the connections. That's it. We now have triangle up and triangle low. Let me give some values to the resistances. I'll make them all 10K. For now, all 10K. I'm not giving any gains. 10K, 10K. So also for the other differential amplifier. So this differential amplifier also I am giving all the resistance values as 10K so that the gain is unity for the difference. So this is regular difference amplifier. So this triangle up and triangle low. So this is what you have. Now I need to have the PWM. I will need to make some more space, and then I will copy and paste one here and one more here, and I am going to delete this part here. Okay, so that it is cleaner, and this is also not needed because I have the modulating signal all shifted that side. So if I move this down and do some rearrangement so that it is neater. So I have the top and the bottom, right? Top and the bottom like this, and because I have the label here, I can use that label and have only one modulating signal coming in picture there. Okay, so now for VG1 I am going to give Vm positive, and here I will give V triangle upper. So I will take this, copy and paste it here and then place it there. And then V triangle lower. Now I will remove this. I will give the modulating signal to the negative and V triangle lower to the positive, like this. This is what we discussed, right? So ready to make the connections. Let me make this connections. Triangle upper, modulating signal, triangle lower. So we are done. So I can say that this is G1 and this is G2. So this should give you the PWM of top and bottom with dead time. So dead time adjustment I can do it here by giving, instead of 10 plus 1, 10.1, I can give 10.2, 10.2 here and get a different offset. So this way I can adjust the offset by adjusting these resistances, and that will imply in effect the change in the dead time value. So let us simulate and see these waveforms and see how the dead times are generated and what is the effect. So what am I seeing here? I'm going to see the two triangles. I want to see the two triangles, the modulating signal VG1 and VG2. So this one, triangle up and triangle low. Triangle up and triangle low. So I am seeing triangle up, triangle low, modulating signal VG1, VG2. That's it. And let me save. Netlist, export netlist. Let me export netlist to pwm analog.car. Let me save that. So when I go and open pwm analog, double click on that, you will see the entire .cir file with 4 op-amps and the updated circuit. So let us simulate this in ngSpice. We call it in ngSpice and check the waveforms. So let me bring in the command window and let me type ngSpice pwm analog.cir and see what happens. So you see the waveforms here. If I amplify, you see again that due to the resolution there is a clipping. I will increase the resolution. But you see that there are two triangles, upper and lower, that has been created. V upper and the blue one is the V lower. VG1 and VG2. Again, you can see that the resolution makes it not so good. So let me improve the resolution and then we can again look at this. So let me redo the analysis, tran, with 0.1 microseconds, 200 microseconds and UIC. And now I will plot V of G1 and V of G2 and see the plot. So now you see that the improved resolution, you see the non-overlapping PWMs. VG1, the red one, is the top gate drive waveform. VG2, blue one, is the bottom gate drive waveform, and the dead time has provided by the offsetted upper and lower triangles. Now this does not have the clamping circuit. We have not incorporated the clamping circuit, otherwise we would have got it from 0 to 15. We can incorporate the clamping circuit to see the clipped or the clamped waveform. So I will leave that to you, leave it to you as an exercise to go to the schematic, incorporate the clamping circuit, resistor, capacitor here, and see that the resistor diode here, which will clamp the PWM waveform going from plus 15 to minus 15 to plus 15 to 0. So this exercise I will ask you to do that, and I will come back here, and if you want to repeat the exercise, change the resolution, the max step size to 0.1 microsecond, so you will see that the waveforms will be correct. I will save that. Let me export it, netlist, export netlist to PWM analog, save it. And now I can go directly to the command window, exit this, run PWM analog again. Then let us zoom this and see that the triangle upper and lower is so much more improved because of the better display resolution. And you can also see the green and the pink waveform here for VG1 and VG2 to see that there is no overlap. So I will leave it to you to complete the circuit with the clamper, resistor and diode, and display the output, PWM output, from 0 to 15 instead of minus 15 to 15.